Welcome to another video from Creative Learning Resources. This video is an edited recording with one of my students. As a respect to the privacy and identity rights of my student, I have removed all conversations and discussions with my student during the lesson. Okay, so topic 7, equilibrium. And in the equilibrium, we actually talk about as we have two reactants. These two reactants, they include A and B. At the start of the reaction, once the time is equal to 0, what is the concentration of A? That is maximum. That is what we have put in the beginning. Nothing started, like, A has not started reacting with B. So the B concentration is also maximum. And the concentration of C and concentration of D. Okay, so that is at the start of the reaction. So we have nothing in terms of C and D, and we have A and B concentration maximum. Now, the forward reaction in the start of this whole process, that will be very fast. Okay, that's at a very fast rate in the beginning, in the start of the reaction. You can understand that this is fast. As the time lapses, the concentration of A and B are decreasing. And why are they decreasing? Because they are being used up. They are turning into C and D. This is fast and getting slow with the passage of time. This is what we have said that. So this is getting slower, but will never reach down to 0 because F, which is the rate of forward reaction, is much fast in the beginning. So at time 0, the F is much bigger than B. While as the time lapses, like let's say time 1, the F is faster than B. Time 2 second, F is faster than B. Let's say time 3, F is equal to B. If we add C or D, if we are adding more product, or you can say add C and D to the reaction mixture at its equilibrium, then the F will become, this addition of C and D will make the F getting slower than B. So it means that it will be like, as we have said, that F is far greater than B. Then with the time passes, it is like this, and a time will come once it will become equal. That's all. That's the end. That's the equilibrium reached. Now, whatever we're going to do, that's we're going to disturb the equilibrium. If a reaction has entered to the equilibrium, so at this point, the equilibrium is achieved, or we reached to equilibrium. And normal circumstances, as mentioned, like, F can never be like that. It's impossible. If we do not do anything, if we don't disturb the equilibrium. Equilibrium means once the concentration of the reactants and the concentration of the products, they stop changing. I'm not saying equal. There's another misconception. There's another big mistake which students always do. They say that when the concentration of A and B become equal to concentration of C and D. That is wrong. Let's say we have 1 mole of A and 1 mole of B. At equilibrium, what happened that this is A and B, they're turning into C and D. At time is equal to 0, A was 1 mole per dm cube and B is 1 mole per dm cube, C is 0 and D is 0, right? Let's say at time 10 seconds, A concentration dropped down to 0.6, concentration of B dropped down to 0.4, and concentration of C is 0.5 and D is 0.5. Suppose. Sometimes students, they say that equilibrium is, or once they are explaining, they say that the equilibrium is when the concentration of A and B and the concentration of A and B become equal to concentration C and D. They say that concentration of A and concentration of B is equal to concentration of C and concentration of D. That is incorrect. That is not equilibrium, or it is not necessarily to be happening. We can see that at equilibrium, we are having different concentrations of A, B, C, and D. That is quite clear. That number of moles, they are staying the same. Like, we consumed how many moles of A, number of moles consumed. We consumed 0.4 of this and we consumed 0.6 of this. And the total of this will be equal to the number of moles which are being formed, which is 0.5 plus 0.5, which is 1 mole. And we made 1. This D not necessarily to be a physical product. This D could be heat as well. There's another thing which we have not mentioned. Like this is like this. We always say that every reaction is having a delta H value. The rate
Yes.
of forward reaction is, let's say, negative 274 kilojoules per mole. That is for forward reaction. Releasing heat, because it's an exothermic reaction, the forward reaction I'm talking about. So that heat is actually used up to do the backward reaction. It does not require any heat energy from outside. Considering the same reaction, considering the same condition, considering the same value of delta H epsilon negative 274 kilojoules per mole, if I heat the container, what will happen? I have the container, and at equilibrium inside the container, I have A, B, C, and D. In the reaction container M, I initially put A and B and I allowed them to react with each other. And then finally, after T is equal to 10 seconds, after 10 seconds, I reached to my equilibrium. I have A, B, C, and D in some concentration. Question is, if I heat at that time, it's going to increase the rate of reverse reaction. And then quantity of A and B will start decreasing. There's a reason. Before understanding the effect of heating a forward exothermic reaction, I ask you a question. I have two reactants. I'm reacting them. I'm getting the products. That is in the reaction mixture at equilibrium. I have all these four guys over here. I have C, I have D, I have A, I have B, right? If I add more D, what will happen? Rate of reverse reaction is going to increase because you're increasing the concentration of one of the products. Now look at this green equation. Like if, what I mean to say, if you look at the energy graph, and then if you place A and B are here, and then they pass through this high energy hurdle, and now they are making C and D. And this is the heat which is released. And if you will be heating that reaction container, which we are going back over there, if you heat this particular container in which heat is also one of the products, this is going to favor the reverse reaction exactly in the same way as you said that in the big yellow rectangle, if you add D, it means that you're adding one of the products. Increasing the heat, in this case, it means that we are going to make a rule. The rule is that for exothermic reactions, heating the reaction mixture at equilibrium is going to increase the concentration of reactants because heating the reaction mixture is going to favor the reverse reaction because the heat is one of the products. And if you're heating the reaction mixture, it means that you are adding the products. If you add more product to an equilibrium mixture, the reverse reaction is favored. If you are heating the reaction mixture, the possibility or the probability or the ability of the A plus B to quit heat or to release heat, that is going to decrease. They will not be able to do that because now it is already too much heat over there. They cannot be producing more heat. They cannot be releasing more heat. So that's why the reaction will proceed in such a way that the result would be, because now it's quite logical as well, because now we know that the guys in the green rectangle, C plus D, if you look at that reaction, in order to they going back into A and B, they have to cross this high energy hurdle. It means that in order to turn for C and D going back into A and B, they have to have this much energy. Because of the external heat provided by you, they are going to have that much more energy and they can more easily be turning into A and B. Double-headed arrow is indicating the energy of activation for C and D returning back into A and B. So this is
Right.
another aspect. This is another way of understanding what is happening if you are heating a reaction mixture where the reactants and products are at equilibrium. What is going to happen and how the equilibrium is going to get affected. The simplest way, which I always tell the students to identify what's going to happen. check that which reaction is exo and which is endo. If forward is exo, then of course, then you write down for your understanding on a piece of paper or on your question paper, on your test paper, whatever you have. So let's say I have another reaction. In that reaction, it's A and B, and then they told us that for the forward reaction, we have C and D, and the value of delta H epsilon is positive 78 kilojoules per mole.
Okay, so unfortunately, after this point, my student requested for a 2 minutes break, and the student returned after a pretty long time. And I put the recording on pause, and then I forgot once the student came back. So I do not have a recording of the lesson after that point, but I have the whiteboard pictures. We're going to use the whiteboard pictures to complete this topic. So considering this endothermic reaction, if we consider that the energy is taken in, which means energy is absorbed during the forward reaction, heating this particular reaction means basically we are adding the reactant, because heat is one of the reactants. For the endothermic reactions, heat is the reactant, like heat is needed to favor the forward reaction. If we heat the reaction container or reaction mixture, this is going to increase the rate of forward reaction. So the forward reaction will be favored, because in order to have a forward reaction favored, once it is an endothermic reaction, the activation energy EA is pretty high. So the reactants have to pass through that high energy hurdle. Heating the reaction mixture is going to provide that high energy hurdle, or to help the reactant to cross that high energy hurdle. On this particular board, we are going to look into the Haber's process. In the Haber's process, 3 moles of hydrogen molecule, which is gas, is reacting with 1 mole of nitrogen, which is also in the gaseous state, and making 2 moles of ammonia. The ideal temperature for this is around 450 degrees Celsius. As it is an exothermic reaction, we can see that the value of delta H is negative, but increasing too much temperature is definitely going to favor the reverse reaction, and the productivity is going to decrease. So the amount of product is going to decrease. Decreasing the temperature is going to increase the amount of product, but the problem is that at a very low temperature, of course, according to the collision theory, the reaction rate is going to slow down and the amount of product is going to form, but it's going to take much longer time. While the equilibrium is also affected due to the pressure. Whenever we are dealing with the reactants which are in the gaseous state, and if the number of moles on the reactant side are different than the number of moles at the product side, affect the equilibrium. Notice at the number of moles at the reactant side, there are 4 moles which require a total space of 90.8 dm cube, while there are only 2 moles on the product side. It means that if we increase the pressure in the reaction container is shown over here in this reaction mixture, which is actually a cylinder with a frictionless piston. This frictionless piston is going to help to increase the pressure. We are putting our weight of 2 kilograms, which is exerting a 20 Newton force downward. The piston is at the position number 1, so there is more space. An additional 1.5 kg is going to exert more force, downward force. This is going to increase the pressure. The piston, the frictionless piston, is going to move down to position number 2. And this is going to reduce down the space available for the gases in the reaction container. So less space will force the reaction towards that side, which is helping us to occupy less number of moles because they require less volume. So in this particular case, increasing the pressure is going to favor the forward reaction. So we are going to have more products, but increasing the pressure too much is not feasible because it is extremely costly, because in order to maintain a very high pressure, we should have a very sophisticated equipment which can help to maintain a very high pressure. And in order to keep maintaining very high pressure, the cost is going to increase a lot. So it will not be very favorable in industry. Okay, on this board particularly, I asked the student to look into a reaction for N2O4 at an equilibrium. Initially, we used 1 mole of N2O4, and the equilibrium concentration is 0.8 moles per dm cube, while the equilibrium concentration is actually 0.4 moles per dm cube for nitrogen dioxide, the product. If we increase the pressure, as we can look into that we have 1 mole of N2O4 turning into 2 moles of NO2, it means that increasing the pressure is going to favor the reverse reaction, due to which, as the pressure is doubled, the number of moles of N2O4 which are reacting are going to reduce down to half. It means that now just 0.1 mole per dm cube will be used up, going to produce just 0.2 moles of nitrogen dioxide. On this next board, I discussed with the student how to calculate the value of Kc. Kc is the equilibrium constant, which can be calculated by multiplying the concentrations of the products with having the powers or the power sign equivalent to the number of moles of the products. Like we have just 1 mole, so the power of D is just 1, and dividing it by the products of concentration of reactants, and the power signs will be the number of moles. Like we have 2 over here and we have 3 over here. There's a lot of mess over here on this slide or whiteboard because I was discussing extensively with the student, so just bear with that. So this board is representing Le Chatelier's principle. My student is having French background. He actually taught me how to actually pronounce it. Its actual pronunciation is, I will try to do it as close as possible. That is Le Chatelier or Chatelier, something like that. I tried to pronounce it the way in which it should be pronounced. So this is a French guy, the Le Chatelier's principle or Chatelier principle is that if a system is at the state of its equilibrium, a small change in the equilibrium, like any kind of change, this change could be an addition of any of the products or any of the reactants. If we are adding the products or reactants, this means we are disturbing the equilibrium. This tends to shift in a direction so as to minimize the effect of that change. It means that the reaction mixture or the equilibrium mixture is having an ability to establish the equilibrium again by moving forward or reverse, depending upon the type of move which we have done. For example, if we are going to remove some of the C, then obviously the forward reaction is going to get favored, so more of the C could be produced to compensate the loss of the C due to our action. Similarly, if you're going to change the pressure, if the number of moles of the reactants and products are different, this is going to affect the equilibrium, but then the equilibrium will be established again after moving forward or backward or reverse. Eventually, the equilibrium will be established, and the same effect with the heat. If it's an exothermic reaction, so increasing the temperature is going to favor the reverse reaction and vice versa. On this whiteboard, I discussed about the phase equilibrium, in which some liquid is placed in a container, which is a conical flask in this case, in which some water, which is in the liquid state, is kept inside. In the beginning, in the start, we have a lot of liquid water inside, which starts turning into water vapors. The water vapors which are forming, so it's turning into the gaseous water, like the water vapors. So the rate of the forward reaction in the start is pretty high, and the water is going to increase. More number of water vapors are going to form, but a time will come once the number of water vapors, they are too many, and they're going to increase the vapor pressure a lot. So due to increase in the number of water vapors which are returning back to the liquid, they are going to increase. It means that the equilibrium is established once the number of gaseous water vapors are going to turn back into the liquid water molecules. That is the phase equilibrium in a closed system. So a closed system means the particles or energy that's not going to enter or leave the system. That's pretty much it. And this is actually a question which I tried to solve with the student, but the student probably got really too tired. So the student just escaped. Just to give you a hint, like an ethanol is reacting with ethanoic acid, and we are going to get our product, which is ethyl ethanoate and water. At the start of the reaction, we have just 0.50 moles per dm cube of ethanol, and we have 1.00 moles of ethanoic acid. At the equilibrium, we got 0.42 moles, which is like, we know that molar ratio is 1:1. So we have 0.42 moles of ethyl ethanoate. It means that 0.42 moles of the ethanoic acid is being consumed. So how much ethanoic acid do we have? that is 1 minus 0.42, which is equal to 0.58 moles per dm cube. This is the concentration of ethanoic acid at equilibrium. Similarly, 0.42 moles of the ethanol are being consumed. So subtracting 0.42 from 0.50, we get 0.08 moles per dm cube. And in order to find out the value of Kc, the concentration of the products, which is 0.42 multiplied by 0.42, you can take 0.42 squared as well, divided by 0.08 multiplied by 0.58. That's how the answer is 3.8. There's no unit over here because all of the values are moles per dm cube and it's all 1. So there's no unit because they're all cancelled out. That's pretty much it. And that's the end of this topic. I hope that you enjoyed this recording of an actual lesson. I know it could be much amazing if the discussion with the students will also be included, but for the privacy and identification rights, I don't want any of my students' voices appearing in any of the videos, even with the consent of the students. There is a possibility in future I may include some of those lessons after taking the consent of the student, but at the moment myself is not feeling comfortable. So all the best, and hopefully you will get advantage from this video. Use your textbook or study guide and solve the questions from the classified booklet, classified worksheets, or past papers. Please don't forget to subscribe the channel, press the bell icon for the latest updates, and drop a comment or any questions in the comment section below. Thanks a ton for watching. Hope to see you again soon.